Hello, in this video we'll continue talking about equidistribution. Let's shortly recall the main things. So for now we'll mainly work with a finite set S, and we have a sequence with values in this set, and we call it equidistributed if every subset of the finite set S eventually gets its proper share, meaning that if we look at the number of elements in the sequence which are in the subset and we divide it by n, this will eventually go to the cardinality of the subset divided by the cardinality of S. Okay, so last time we wanted to prove a theorem in the case where S has cardinality of prime, so we can assume it's C modulo PC. Let me first tell you there was a small mistake. So namely, so the claim is that this is equidistributed if and only if this exponential sum of e to the 2 pi I k sj divided by p, which we will also call EP of k sj, is in small o of n. So it means if we divide it by n, asymptotically it will go to 0. And there was missing a p, and it was in the denominator, and it was missing everywhere. That's important, otherwise the theorem is false, which you can already see because otherwise we just sum ones, and a sum of ones is always n. It's never going to be in small o of n. Also, we had some intuition. So if we sum up these roots of unity, then they will, if everyone gets its proper share, they will gravitate towards the center, and then they will be in small o of n. And the converse is also true. So if this holds for all k in 1 up to p minus 1, it will be equidistributed. We proved one part of this theorem, of course with the small hiccup that there was the divided by p missing. And now we're going to prove the converse. So namely, we assume that the sum is in small o of n for all k in 1 up to p minus 1, and we show that it's equidistributed. So let's start. So let's assume that the sum from j equals 1 up to n, now EP of, and what do we want? Sj times k, or maybe I call it k times sj, but it doesn't matter. Yes, let me also call it k times sj, I like it more. K times sj. Let me remind you just so that you don't forget. So we have this sum here. This should be in small o of n for all k in 1 up to p minus 1. Maybe also note for k equal to 0, of course, it can never be in small o of n, because then we sum ones again. Okay, so that's our assumption. Now let's do kind of the simplest thing we can do. Let's sum all our equations up. So j equals 1 to n EP k sj, and well, since the prime p is fixed, this is still in O of n. Okay, so we have this. Now let's try to get rid of this k times sj. So in order to get rid of this, we introduce a third sum. So we have these two sums. We sum up some values. Now let's introduce an artificial third sum. And so it goes from 0 up to p minus 1. And we just want to capture the ones where k times sj is equal to L. And then we can say, okay, this is EP of L. Okay, so this is the same thing. Now let's switch order of summation. And we do it in the following way. we sum the j's, we sum L, and now we sum the k. And Sj is equal to L, E, P, L. Now let's analyze this expression here. So now we have to be a bit careful. So let's start with the case Sj is 0 and L is 0. Okay, so in this case, k can be anything. So any value from 1 up to p minus 1 satisfies the equation that k times Sj is equal to L, so we get p minus 1 in the sum. On the other hand, let's say Sj is 0 and L is non-zero. Well, whatever we do, it will never be satisfied, so the sum gives 0. Okay, so we have more possibilities. Let's say Sj is not equal to 0, but L is equal to 0. Well, again, this can never happen. And finally, Sj non-zero, L non-zero, and recall that we are dealing with a field, so this has a unique solution. Okay, so now let's deal with it and see how this changes our expression. So we can basically, we can pull out the term for L equal to 0, and so for the L equal to 0 term, we get p minus 1 many solutions, and these are exactly, but we only get one if Sj is 0. And also note that if L equals to 0, this EP of L is 1. So we get p minus 1 times the cardinality of the, let me call them j, yes, j in 1 up to n, with Sj equal to 0. So this is our first part. And now we got rid of the L equal to 0 part, and of the correspondingly of the j's where Sj is equal to 0. So what we are left with is the sum from j equals 1 up to n, where Sj now is non-zero, and the sum from L equals 1 up to p minus 1, and we are now dealing exactly with this last part of our case distinction, so we get exactly EP of L. Now we use orthogonality of characters again, and this tells us that if we would sum from 0 up to p minus 1, we would get 0, but now we sum only from 1, and EP of L is 1, so this sum is actually equal to minus 1. So let's pass now everything, so the whole thing is now equal to p minus 1 cardinality of the set of the j from 1 to n, where Sj is equal to 0, plus, minus, because we have the minus 1 from the sum, so minus, well, I don't need the 1, and now we sum a bunch of 1s, and how many 1s are these? Well, these are exactly the j's, the number of j's for which Sj is not equal to 0. Okay, so now we have these two things, and we can kind of compare them. And recall that this is in small o of n. So now we are getting close to what we want to prove. So let's compare these two things. So these two things are everything. So the cardinality of j in 1 up to n, where sj is 0, plus the cardinality j from 1 to n, where sj is non-zero. This sums, of course, to n, because this is everything. Now, let's call this equation here 1, this equation here 2. Now, if we add these two equations together, we get p times the cardinality of j in 1 up to n, where sj is 0, is now equal to n plus small o of n. Well, and now let's finish it almost off. We still have a small argument to do, but this basically proves it. So the cardinality of the set of j in 1 up to n, where sj is equal to 0, divided by n, goes now to 1 over p. Because if we divide by n, this part goes to 1, the small o of 1 goes to 0. So if we divide by p, we go to 1 over p. So now we have basically proven it. The only thing we have to get rid of is this sj equal to 0, because we only proved it for one subset, but we have to prove it for all size 1 subsets. So in order to prove this, we look at the following. So to get, let's say, okay, let me see how we write it. So if we want to have the thing 1 up to n, sj equal to, let's say, a, divided by n, that this goes to 1 over p, replace sj by sj minus a. So if we do this, then we get an sj minus a here, and sj will be a. So what we still have to check, okay, so let me write it, sum j equals 1 up to n, e p of sj minus a. Okay, so now let's just shortly analyze this. So EP is a homomorphism similar as the exponential function is. So for, it sends plus 2 times. So homomorphism from, well, depends on which group you want to work with. Anyway, it's we get the multiplication, so we get sum j equals 1 up to n, ep sj, ep minus a. This is the ep minus a we pull out. Sorry, sum j equals 1 to n, ep sj. Well, and this is also in O of n, well, we should have done a k times sj minus a. Okay, let's do it like this. We get a k times sj minus ka, ka. In any case, this is a small o of n for all k in 1 up to p minus 1, which means we can apply what we've proven so far to sj minus a, and we get the conclusion that this converges also to 1 over p. And this proves the theorem. Okay, thanks for your attention. I'm not sure in which direction I'm exactly going to continue, but I hope you enjoyed it. I certainly did, and have a good time. Bye.